already. We turn over. There's that old joke where people say that since we turn over our bodies about every 48 hours, if you look at your wife, at least did you know that in 24 or 48 hours, half of her is going to be lost and exchanged. So the only part that you worry about is that the mind doesn't exchange so quickly, and the heart muscle doesn't exchange so quickly. So you worry if there's a problem with the heart or the mind, but the rest of the body is only temporary.
Yeah. Have people used sort of infrared spectroscopy to sort of study this? Because, I mean, infrared spectroscopy gives you a lot of information about structure, three-dimensional structure, environments that functional groups are in. Yep. And it kind of went out of fashion when NMR came in.
People are using two-dimensional IR for looking at the structures of small peptides, and wanting to use that actually to fit to these sort of simulations. The difficulty is that the force fields that we use, where you take constraints and simple harmonic ones for angles, really do not reproduce vibrational spectra at all well. And the other thing is that does the fine detail of the conformations of a dipeptide, are these really relevant when we're looking at the structures of a protein with effective force fields? We can be completely wrong at the dipeptide level, but still keep lysozyme beautiful. But this is, people are using it. People use two-dimensional IR spectroscopy in order to exercise some of these ones.
Because there's a paper recently, I think it's in Nature, where they were looking at infrared spectra at very short time scales. And so, if you're looking at the difference in structure on those short time scales, then perhaps that's a way of feeding into your simple systems to do that.
I mean, all of it's good. I mean, all the data gets combined. It was just, as I say, I mean, when people are constantly talking about femtoseconds, and we worry the fact that if we can't get to hundreds and hundreds of nanoseconds or microseconds on these little systems, we're sampling not the complete set of appropriate states. So it's a balance. So what you measure on a femtosecond is really going to be not an ensemble of dynamics. It's going to be an ensemble of different protein structures that you have to consider to get it correct. But
and I have a question. You mentioned this model. I noticed this is origin coming and most is on Melanin.
The what?
The model you say this peptide coupled to memory protein. So I talked to Huang. He's been doing Melanin for ages. So he mentioned to me that model he published by his journal, which is pretty solid as by experiment. So my question is, it is cases different, or it is truly observed by experiment without the textbook involved? You know what I mean? The Melanin case.
But it wasn't Melanin.
Yeah, I know it's not a Melanin. I mentioned the Melanin case.
I think if I took Melanin, that's a much better evidence to say that it's really helical in the membrane. Okay, so it's going to depend vastly on what the particular peptide is. Now, but yes, Melanin is really good. So probably if it's nice and kinked, it could very well lie around these knots. But still, you're looking at the structure of individual peptide in the membrane. You're not really looking at the pore which is formed, or the dynamics of it. But as I say, Melanin is very different to Melanin. It's much less structured than Melanin, and I would have made a one-to-one comparison. Now, what's been going on now is, of course, taking a whole series of systems with more structure and less structure and seeing whether they all form pores in a similar manner. And of course, they probably go very good.
Okay. So the next one is from the physics department, UQ, and Tata is here. So you have 10 minutes, right? But you can take time. Okay. Go ahead.
All right. Thank you very much for the organisers to allow me to talk here today. So that's me, I'm a real person, and I'm just going to talk about condensed phase melanin and its charge transfer properties. And in particular, I just want to tell you, if I can, just one thing today. If we were to take solid-state melanin, put it in the Kuhn conditions, the dominant charge carrier would be a proton. and that would be in contradiction to the idea that it is a semiconductor. So how am I going to go about telling you this story? Well, I'm going to just review the evidence, the dominant paradigm of why people thought that it's a semiconductor. And then I'm going to throw out some issues with the semiconductor model, which you can find in the literature. And then I'm just going to review the evidence we collected last year on the humidity dependence on conductivity, put it all together in a transport mechanism, and then I'll just conclude what I've said. So, just to remind ourselves, that's the basic Melanin monomer unit. And if you forget it, you can also just check the bottom there. Very nice picture. So, why do people believe Melanin is a semiconductor? Back in 1960, Longjeet Higgins said, well, if we look at Melanin's absorbance, we can sort of explain it if we say it's a amorphous semiconductor. But it was a decade and a half later when McGinnis said, published this piece of data, which demonstrated electrical switching behavior with the melanin. And this is a definitive piece of data that people still use today to say melanin is a semiconductor. But this is not the only evidence. If you put your melanin under a vacuum and do a thermoelectric measurement, you get a negative charge carrier. Negative charge carrier, that's an electron, that makes perfect sense within the semiconductor model. Also, as you increase the temperature, you increase the conductivity. Classic semiconductor behavior. However, if you are willing to look through all the literature, there are some problems. If you do if you look at Hall and thermoelectric effects at, say, Euclidean conditions, you get a positive charge carrier, which is not typical of a semiconductor. Why would you go from a vacuum to laboratory conditions change the sign of your charge carrier? Furthermore, people have observed non-ohmic behavior, and that's due to space charge polarization. So I'll come back to this later because this is something we observed and explain what that means. Powell et al. Now, this is not Ben Powell, which is in the back there. This is way before most of us know it. Did a coulometric study on. You better be careful here. The thing is, they hydrated melanin and they did a coulometric study, and they determined that protons are the charge carrier, which is certainly not a semiconductor behavior. And then all of this comes together and say water plays a key role in conductivity. And someone, I can never pronounce that name for the life of me, did a humidity dependence on the conductivity. However, they had poor control on the hydration. They tried to use salt solutions to control humidity conditions, which is very bad. And they assumed that the humidity is proportional to the water content within melanin, which is not correct. So, what did I go and do last year? Well, in order to determine the conductivity behavior as a function of water content, I had to determine what the water content is within melanin. And that's basically what this graph does. If I've got a relative pressure of water, how much did I gain in weight? And as you can see, it's not a linear relationship. There's an initial increase and then it flattens off. And after fitting this to a theoretical model, I can put an upper bound on the specific surface area, which is about 550 meters squared per gram. So basically, it's quite a porous substance. Using that absorption isotherm, I went and determined the DC conductivity of melanin as a function of water. And this is the data I obtained. As you can see, I've got 3 different curves. That's 3 different samples. This graph here is just for a function of relative pressure, and this is just renormalized to 1% gain. And as you can see, we've got a rapid increase in the conductivity after about 0.4 relative pressure. Some of you, if you look through the literature, say, well, semiconductors, if you hydrate them, if you are able to hydrate them, they will increase their conductivity. Because all you do is when you add water is you increase the dielectric constant of the environment, and that just lowers the band gap energy. But if it was a semiconductor, you'd expect that kind of behavior. You'd expect an immediate response and then a flattening off of the conductivity. And this is not what we are seeing. In fact, we are seeing something akin to percolation theory. So if you don't know what percolation theory is, I'll come back to that in a moment. But suffice to say, it doesn't look like it's a semiconductor. Get all of those conductivity data points, I got lots and lots and lots and lots of voltage data. And this is a typical curve I've got. And you see, so there's the linear bit, that is if this was obeying Ohm's law, all of the data points would be lying on that flat line. And initially it does, but then at high voltage, it starts shooting up. And usually this is a signature of what is called space charge polarization, and this is due to ionic carriers. So if you don't know what that means, if we just imagine two electrodes, and we've got ionic carriers in our system, and we put a potential across, all the ionic carriers will start aggregating around the one electrode, shielding that electrode from the other electrode, causing an increase in the resistance or a non-linear behavior in the current voltage data. So from the data that I've collected, I said, well, there looks like there's an ionic carrier. The literature suggests that there's an ionic carrier, and the behavior is percolation theory. So how do I put all those things together? First thing is I have to have a guess at what the ionic carrier is. The most reasonable one is the proton. And the reason being is if I put a lot of water in our melanin matrix, water can solvate off protons from your alcohol groups and your carboxylic acid groups. So that's where your source of protons come from. And so when you put a potential across, we can think of our system in a macroscopic view as a percolator system, which is schematically shown here. So if we just imagine that melanin is a smooth background and the backside has nothing to do with the conductivity. So this is not true, but this is just an assumption we're making. All these little dots we can present water molecules, and the bond between the water molecules is just interactions between the water molecules. And if we have enough water in the system, we can form a continuous chain from one end to the other, and we get a response. So now we all know that water is notorious. If you take all the ions and stuff out of water and just have pure water, it doesn't conduct electricity at all. It's terrible. So what is it conducting? Already I've said, well, we have a source of protons from the melanin itself, but how will the protons move from one end to the other? And how we explain it is something called the dropless mechanism. And you can see it being explained right here on this little animation. If we've got an H3O plus molecule and just pops the hydrogen off to the next water molecule and just move it along a chain. So that's how we think what is occurring in melanin when we hydrate it with water. So, conclusion. Long-standing view is that melanin is a naturally occurring organic semiconductor. And there's good reason. We've got switching behavior, we've got negative charge carrier, negative sign of charge carrier at vacuous conditions. However, when you hydrate things up, we get evidence for proton charge carrier. So, and that is from our data, the increase in conductivity as a function of humidity. And that hypothesis explains some of the anomalous data you get in the literature. So, in conclusion, just getting back to what I was trying to tell you at the very start, that the dominant charge carrier in melanin at ambient and high humidities are protons rather than electrons. So, two questions for this workshop is one, how does the structure of melanin lead to this kind of behavior? And two, I forgot the second question. All right, then that's it.
So we have 10 minutes for questions. Wonderful talk, okay. Yeah, wonderful talk.
I thought it was a 10-minute talk.
Yeah.
Surely we all get 10 minutes more free time, so that's all right.
Just ask a question. Why is melanin unusual in that case? Because we would you expect any solid protein or hydrophilic materials to behave in a way?
Now that's a good question to ask. A guy called Rosenberg in the 1970s tried to map out how proteins would respond to hydration. And most of the proteins he found were basically semiconductor behavior. I know of only one organic system, collagen, that maybe ate like this, but I haven't looked into that, so yes and no is my answer.
Actually, on that point, the person who began the study of semiconduction in proteins was Healy in England, and so he took the proteins and found that and then, of course, the drier the proteins became, the less they expand. In fact, the proteins generally have band gap, high band gap. So it, in fact, what you was looking at was as a result of water. You get the dried out substance, in fact, conductivity of water.
Yes, that sort of conduction in water usually involves chemical reactions with the two electrodes.
Yes.
Do you see anything like that here?
Well, no. That's the colorimetric studies that are there that you probe that. Exactly that. You see where the hydrogen gets involved at the electrode, and then we correlate it all to see where the kind of charge carries on. You have to have the right equipment, which we don't have. And you need guts, which I don't have. This was, I don't know.
No, we're not doing it.
Dang it.
Oh, no, you first. I think you.
Yeah, no,
you first. Oh, okay. No, after you. No. So can you just expand on the colorimetric study? What was done exactly, and it's also somewhat old. Has anybody tried to reproduce it? It's older than anybody in the room, as you were saying.
Well,
you should take that as a compliment.
So a colorimetric study, what you do is you assume that protons are conducting. So what you would expect is, as the protons get to the one electrode, they will annihilate and produce hydrogen, and the other side you get oxygen. And so if you then assume, if you look at what the reaction should be from Faraday's law, and assume you've got 100% protonic charge carriers, you should expect a certain amount of hydrogen. And the less you get, the less the proportion of the protonic charge carriers within the system. So that's the basic principle of the experiment. People trying to reproduce it, I've not seen anything like that at all. It's a pretty hard experiment.
Yeah. So, whenever you took the protein was salt-free, right? No buffer salt was there.
No.
It was completely
what I did is just
dialyzed or something like that.
Yeah, no, it's just a powder, which I just pressed through.
It's a powder, but the protein lyophilized powder will contain the salt, buffering salt.
All right.
So, I'm wondering whether that conductivity due to this some ionic conductivity.
No, we thought that might be the case in the experiment.
Did you do some controlled experiment on
Yes, I did.
on salt?
Yes,
like
I added
phosphate buffer salt or something.
Yeah, I just added sodium chloride to see if I then reduce it all out, where I get an increase in conductivity, and it's minimal. It doesn't explain that trend at all.
Okay, this is number one. And then, did you do some kind of controlled experiment varying pH, like in a higher pH value, for example?
Higher what?
pH.
pH. Oh, well, it's a solid.
There is no proton and something.
Well, this is a solid state. I don't know how you control it. Only thing I controlled was the humidity.
Yeah.
That's the only thing I controlled.
The control experiment is one where you block those proton sites. So, for example, you produce a 5,6-dimethoxy, where you block those sites. And in fact, Bernie's not going to do that experiment. Another student is. This year, now that we have the dimethoxy polymer.
You are going to do
so yes, we will do it.
Sorry, so you mean that there's a site, a putative binding site for the water?
Yeah. So if you block that binding site, the 5,6-dimethoxy N-methyl is a good model compound for that. And we have that, and we have a polymer of it now. So that's the exact motivation.
Very good experiment. Yeah. And another stuff, like if you have no effect of the buffering salt, for example, so use a buffer salt and protein mixture and control the humidity. So in the water or the solution, whatever you will get, that will get the different pH. So that I would.
I understand it. I understand it. Yeah.
So you don't have to do the sophisticated experiment like blocking proton sites, something like that.
You were noting Longer Higgins there, but I didn't mention it yesterday in my talk, but Longer Higgins was the first person to assign porphyrin the spectrum. And he's sort of very famous for that, but in the year he put that paper out in 1960, he came to the conclusion that all worthwhile problems in chemistry had been solved, and he was appalled by the advent of the digital computer. And he was sort of an anti-Alan Marx. So he said that if that's what you've got to do to stay in chemistry, he was out of there. So he ended up moving into brain research, wasn't it? Yeah, so so he made quite a name for himself in a completely different field as a result of the digital computer.
He also discovered the so-called very geometric phase. He discovered that like 20 years before Berry.
Oh, really?
You have a question?
Can you just tell us the vertical scale of your conductivity? What was it going from at low humidity to what did it go up to high humidity?
So, scale is Siemens per centimetre?
Yeah, or is it times 10 to the minus?
10 to the minus 7. So it's not, it wasn't.
That goes
in many ways.
It's not 1 times 10 to the minus 7, so that will take 10 to the minus 5.
Yes. Historical note here. Is it generally known that melanin is the basis of what is could be regarded as the first working molecular electronic device? The idea of the switching, the electric field, the reversible switching of melanin was discovered by, I think it was
John McGuinness.
Yes,
yeah.
And so his device actually is in the Smithsonian Museum.
It is indeed, yeah. And in fact, John would argue that in fact he does argue that the Nobel Prize that was given to our friend Higa and Shirakawa was misassigned.
He argues that in Wikipedia.
He argues it personally too if you ever talk to him. Because you wouldn't take that point on.
But isn't this raising this data raising the question that he's not really? It is indeed. He doesn't really have a molecular electronic switch.
Absolutely.
He's just switching on and off water.
Yeah. Although, look, of course, there's still the question of what happens at low humidities, and that's sensitive. I mean, I think there is some credence to the fact that you do get local changes in the dielectric constant, which can manifest in a band gap change the gap energy. I think that's probably true. So you could argue both points. In fact, John moreover argues that the former point rather than the latter, that you do get small changes with he saw these changes, but he swept them under the carpet because it didn't fit in the story. And in fact, in the science paper, there's a throwaway comment, which, if you look at it carefully, is exactly this behaviour.
I think it's also in physics, like when I mentioned before. C.D. Ely studied this sort of thing over several decades. Lots and lots of papers about it.
E-L-E-Y?
Yes, E-L-E-Y, D-D.
He also did something on conductivity DNA.
Yeah, that's right.
Lots of his paper in Pethick's book.
Right.
Lots of work in Pethick's book.
Right, yeah, that's in our paper that you included. Yeah, Ely and Spivey.
All right.
Yeah, 62.
Well, you did wonderful work, okay. So let's finally, let's join me to thank all this morning's speakers and all did wonderful work.